this is my final presentation of my internship, and this is my last presentation in this lab. So I would like to present my project, which is based on Mycobacterium tuberculosis prediction using multi-talk mass spectrometry data using machine learning. So tuberculosis is basically a major global health concern necessitating rapid and accurate diagnostic methods. So we have traditional methods such as culturing and PCR, which are often time consuming and labor intensive. So that's where mass spectrometry, which is multi-TOF, can be a promising alternative for rapid and sensitive detection of TB biomarkers. So if we integrate machine learning in this, we can enhance the accuracy and also speed of TB diagnosis by analyzing the complex mass spectrometry data. So according to the current literature produced by our lab, the key biomarkers include CFP10 and ESAT6, which are very crucial biomarkers specific to Mycobacterium tuberculosis. So in our lab, we are focusing on nanodiamond, and as Vaishnavi is also focusing on morph particles in order to extract the biomarker related proteins from the bacterial cultures, so which simplifies the sample preparation and also minimizes interference depending on the matrix we are using. So the specific peaks we are targeting in this study is basically CFP10, the target MIC values, and these SAT6. These are 1, 2, 3, 4. There are total 6 peaks which we are targeting. Alright, so the first thing for my project which I've done is collected the data. So whatever the existing data which was there before I came here, I've collected the data, and also I've gained hands-on experience in order to how do you do nanodiamond extraction with the help of Avi, and also Vaishnavi, and also Mikey helped me. So I'm very grateful for that. So, and the data is stored in TXT files which has MIC and intensity values, which is very raw data. And then after that, the very crucial thing in order to do for a good pipeline is to perform baseline correction. So why do we do this? In order to remove the unwanted noise or the artifacts from the spectra, in order to isolate true signal peaks using ALS method. So this is a method which has a very big mathematical formula, but since I'm using Python programming, there is a package which I can directly use. So I've used ALS method in order to perform baseline correction on the raw data generated by the lab, and then I perform normalization. So what is normalization is basically you have like intensity ranging from 100 to anywhere to 70,000 or 60,000. So if you perform normalization, you can basically reduce from 0 to 1. So we perform normalization in order to standardize our data set quality. And then the next thing which I've done is smoothing the data. So what it does is it reduces the random fluctuations or the high frequency noise in the spectrum. And the very important thing which I have recently noted is the dynamic tolerance calculation. So basically we have the target peak, for example 10,100. So basically I'm extracting the region around that peak plus or minus 50 Daltons per se. Okay, it's 10,100 plus or minus 50. I'm targeting that region first, and then I'm taking the standard deviation of the MIC values using the formula. So we know the standard deviation formula, where sigma is the standard deviation, n is the number of MIC values in that region, and the individual value and the mean value, which is mu, the sum. And then I've calculated the standard deviation of the MIC values within that window, like plus or minus 50. I've taken the standard deviation values, and then I calculated the tolerance. The formula for tolerance is the twice of standard deviation. For example, I got a standard deviation of, let's say, 50. So 2 times of 15 is 30. So I'm taking a tolerance of 30, and the minimum tolerance I've set is 0.5, and the maximum tolerance which I've set is 15. So when you clip it, so basically we'll take the minimum tolerance. So this is the formula which you can use basically. For example, you will take the minimum tolerance. If the tolerance you get is less than the minimum tolerance, then you get your minimum tolerance, and then maximum tolerance when your tolerance is greater than the actual maximum tolerance. So this involves a lot of math. I'll explain later if you're really interested about knowing the mathematical stuff behind this dynamic tolerance calculation. And then after doing the window, so we got the tolerance of the peaks, right? So for example, we got the tolerance of around 15. In that region, what I'm doing is I'm doing Gaussian fit. So the Gaussian function is that, which is peak intensity AE. This is the formula which I've used from the literature. So after applying the Gaussian fit, I have considered three features. So three features are full width half measurement, area under the curve, and the normalized intensity which we have done. And also the presence of peak, whether we have the peak or not. Which there are four features. So since we have 6 peaks and multiplied by 4 features after applying Gaussian fit, we have total 24 biomarker features which I've considered, and these are the relevant formulas in order to calculate the full width half measurement, area under the curve. Alright, so we have overall 24 features, and then after 24 features I have done again 6 global features. So what are these 6 global features? So this is something which I've added recently to train the model. So basically I'm taking the total number of significant peaks in the spectra which has a minimum intensity of 0.1, not the biomarker but the overall spectra. I'm taking the total number of significant peaks. If the minimum intensity is above 0.1, like again in the sense 0.1 in the sense 0 to 1, since I've scaled from 0 to 1, 0.1 I feel is little significant. So I've taken the total number of significant peaks and then total ion current. So what is total ion current is basically the sum of all the intensity values in the spectrum. I've taken that and the mean intensity of that peaks and the standard deviation of those peaks, and then the skewness and the kurtosis. The skewness is basically, there you can see the skewness. So this negative direction, positive direction, and the normal distribution. So what it basically gives you is the symmetry, asymmetry of the intensity distribution. And the kurtosis is basically gives you whether you have sharp peaks or the flat peaks. So that 24 biomarkers and the 6 features, so overall 30 features. So with these 30 features I have trained the model. Alright, so basically after doing all sorts of calculations, I've come up with this 3-4 experiments which I've done for my study. So this have come up in the last month. So basically first I've done the feature engineering which I've done right now with the with this 30 features without SMOT. So SMOT is basically if you have imbalanced data set, you basically add synthetic data which you are not generating. You're adding synthetic data, your own data, and then training to balance the distribution. So I have done without SMOT and then with SMOT, and then non-feature engineered is basically putting the raw data into the model. Whatever data you're getting from the mass spec, you're just putting into the model without any all this feature engineering, nothing, just putting into the model directly. Again with SMOT and without SMOT. So totally 4 different experiments are conducted. Alright?
Can you come back again? What's the blue one you want to, blue and the red ones you want to say? You have a triangle, right?
Yeah, triangle is basically the minority points and the green is basically the major class. In our class, basically, we have more amount of TB data and less amount of NTM data. So when I came here, we had around 900 TB, 200 NTM. Alright, so we need to balance that.
Oh, okay.
So in order to get to amount of TB, I have to generate synthetic data. So those red are basically the synthetic data which are generating based upon the existing data. So this is an algorithm which was devised by some other scientists before, but I'll show you the results. What is the result with SMOT and without SMOT as well. So as I said, the raw data which I've put into the model, I wanted to test if the data which we have, the biomarker data is really good. So first, for the peak 10,660, the coefficient of variance is around 0.06, like that. I've calculated the tolerance basically. In this tolerance range, I've taken the biomarker intensities in order to feed into the data set, which is non-feature engineering, the raw data. So I'm considering this as a raw data, no smoothing, no normalization, nothing, just the raw data. So this is the tolerance which I've found, and for all these peaks I've calculated the tolerance values. So as I said, when I came here, the original data set was 205 NTM and 959 TB was there when I came here. So when I did that feature engineering and all the stuff which I've told, we can actually see the clear difference between NTM and the TB. So 0 indicates NTM and 1 indicates TB. So the intensity at 10,660 peak, basically at NTM you can't see any significant intensity when you normalize. But in TB you can actually see there is a significant difference. And also the area after you put the Gaussian fit and the intensity of 10,100 and the area at 10,100 and the total ion current. So basically you can, for 30 features you can plot, but since there is a space constraint, I didn't plot everything. So since we had the class imbalance, because we had more amount of TB data and less amount of NTM, so there are two choices we have, either using synthetic data or use existing. So if you want to use existing, the problem is that you have more amount of TB data, and then when you're splitting the data, basically you're giving more of TB and less of NTM, which causes bias, which we call overfitting in machine learning. So what I have seen in some other papers is they have used stratified k-folds validation. For example, here we have less amount of female records and more amount of male records. What they do is they take same amount, they maintain same ratio of male and female throughout 5 folds or 7 folds or 10 folds. For my model, I've taken 10 folds, so I've done 10 times in different combinations.
So you mean like they try to diagonalize their data sets?
Yeah.
You can say like this.
Yeah, so if you have imbalanced data set, you can actually perform different combination but maintaining the same ratio. So I've used this. So k-folds is basically the number. I've performed stratified 10 folds cross validation for my experiment. So this is the feature engineering after all the 30 features which I've derived and then trained with multiple machine learning models all in one go. These are around 33 machine learning models and no synthetic data using the stratified k-fold 10-fold cross validation. You can see that the LGBM classifier, like what is that? Light gradient boosting machine classifier. It is in the top. So this accuracy, F1 score, precision, recall, accuracy, and then ROC, AOC is basically the performance metrics of a model. So what is accuracy is basically how many were actually correct, how many predictions were actually correct. And then what about F1 score? F1 score is basically the harmonic mean of precision and recall. So if you ask what is precision, precision is basically out of all the predicted cases, how many were actually TB, alright? And the recall is basically out of all actual TB cases, how many did we correctly identify? So when we train multiple models, LGBM classifier emerged as the best without any artificial data after extensive feature engineering.
So your left hand side, I mean this column means like you have different algorithm.
Yeah, these are algorithm names, and
the
these
right
are
hand
the
side
metrics.
is your training parameters, right?
Yeah. These are the, after training the model, you are testing with the other 10. We are splitting the data, right?
Yes.
10-fold cross validation.
10-fold, yeah.
You are training with 9:1 ratio.
Okay.
9 part is for training, and you are testing with the remaining 1
Yes.
part which we have. This is the raw data generated in the lab already, not by me. This is the already existing data. I'll show you with the current model, with my data, how it acted.
So the score here,
Yeah.
like a 0.979, what do you mean?
Basically, if it is close to 1, it is really good.
Yeah.
If it is 0.5, it is normal, like 50-50. Like you have to multiply by 100. So 97% accuracy, 97.9% F1 score, like that. Yeah. So if all the metrics are close to 1, that means the model is really good, you can say.
Sorry, I have a question. You said that you use 9:1, 9 for training.
9:1.
Did you also try lowering the training ratio, like 8:2, something like that?
No, I've done only like folds, you take we have imbalanced data set, right? You do the same ratio, but 9:1%. And then with SMOT, with the extensive feature engineering, here the CAT boost classifier performed well. And then without SMOT, without any synthetic data, but with the raw data trained, here again CAT boost performed well. Again, when we performed SMOT on the with raw data, again CAT boost performed well. So basically, if we compare all the 4 experiments which I've done, we can see that the feature engineering of 30 features without any artificial data, it performed really well. Here you can see the accuracy is 0.9. So we are not just taking accuracy but also the precision, recall, F1 score. The precision, as I told, is basically out of all predicted TB cases, how many were actually TB. So like 0.88, like 88% of the time it is actually correct. So basically this is the technique which I could say that this technique is really good. This experiment has yielded good result. The extensive feature engineering, no artificial data, and the stratified k-fold method. And then when I saw what are the features that are contributing to the importance of the model, so here you can see 0, the positive side indicates the TB and the negative side indicates the non-TB cases. So as I said, the feature engineering data set without SMOT has yielded better results. So what are those features actually contributing for the better accuracy? If you ask, it is area at 10,660, area at 10,100. All the top 5 features, 6 features are basically accounting for the model's accuracy and the better performance. And now when I did only raw data, only the peak intensities without SMOT, and the performance was good, it was, you can see those 10,660 is the one the model is taking into consideration. Again, with the artificial data, the feature importance was area at 10,660, but without SMOT, the second feature importance was 10,100 area. But here it is taking full width half measurement at 7,974 feet. So basically, if you are giving the synthetic data, you are basically creating noise in some cases. It is not actually good if you create synthetic data in actually diagnostic scenarios, which I feel.
So that's you mean the
My interpretation.
yeah. So you can come back to that. That means like FED with smoke, right? So that means most likely the picker side, if this belong to TB,
Yeah.
okay, they are quite well, right? No matter your intensity or your area,
Yeah.
they all can fit quite well,
Yeah.
right? And how about the right hand side? And NFED,
It
what
is non-feature, raw data. Raw data
Oh,
with the
pure raw data.
Yeah.
Pure raw data, then you have a like kind of more native values, right?
Yeah, exactly. And then the paper which I presented in the last group meeting, so they have also mentioned that the SMOT, if you actually use it in a diagnostic purposes, the performance has reduced by 10%.
Oh,
But
okay.
in my case, when we did it, the accuracy dropped is 77.7%.
Why?
It's
Why?
because you are producing the synthetic data into the data set, right?
Oh, okay.
So the synthetic data which you are generating is not actually good.
Okay, so
Especially in
this
this-
is your conclusion,
Yeah,
right?
correct, yeah. So
So
this-
I remember you also have done your real data, right?
yeah. So the real data which I said, this one, with the performance on the external set, which is generated by me, on that has performed well. No, without any synthetic data.
Okay, the red one.
Yeah, the red one, it has performed well, 0.9, like 90% accurate on my data, which generated by me.
Oh, okay, so this contributes a lot, right?
Yeah.
So that means the synthetic data strategy for AI
It's not actually a
is
right
not
thing on
very
this.
reliable
Yeah,
approach.
not reliable.
You still need to have the
Generate.
real data for your training. Otherwise, you synthetic garbage.
Mhm.
So it's something like in now the AI tool, right?
Mm.
You have the photos, right?
Mm.
You want to remove something, they just take it and take it out. And
Sometimes the useful photos also might get.
also use similar strategy, right? Then regenerate the patterns there, right?
Yeah, correct.
So this is somehow most likely like this.
Mm.
So that means in order, your conclusion is like this. You go to the red one, right? If you want to get a reliable data training set, you need the real data, and also it should be a balanced data.
Yeah, correct. Not always balanced. Even if you don't have balanced data, you can actually use stratified K4. You maintain the same ratio throughout the.
Oh,
training.
okay. Okay.
Yeah.
So this is something you can write and discuss in this analysis. Yeah, okay. Okay. So this conclusion is quite clear.
Yeah, so I wrote this mode actually creates synthetic, like they don't exist in the real world basically, the
Mhm.
data which is being generated. So when I compared with the external validation set, the synthetic data was not able to recognize true patterns in the data.
Mm-hmm.
So what we used, so since we have imbalanced data set, either generate the data on your own to balance the data set, or use stratified K-fold strategy in order to come up
Okay.
with a better thing. And then LGBM classifier is the best one out there.
Okay, so you get a kind of LGBM. So among those training tools, right?
Mm.
So that the trainer is the best one.
Yeah. In that training and testing frame, on my data also it performed well. 0.9.
So other research also have similar thing? No, it depends.
In this paper they have got cat boost as the best performer.
Okay.
They are doing antimicrobial resistance.
Okay. So you can you create something like this? Probably for this kind of biomarker stuff, that
This-
training set probably can be a
Mm.
good choice.
Mm.
Okay.
And thank you everyone. It was a very nice period of my internship throughout. Thanks for giving me this opportunity.
Okay, good. Yeah. You can send me your report also.
Yeah, yeah.